Here we have another example. A rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of its base is twice the width. Material for the size cost $5 per square meter. Material for the base cost $10 per square meter. Find the cost of the cheapest such container. Okay, um, if we said when we are solving for an optimization problem, we can solve the problem by following this strategy. The step one is to draw the picture, and step two is to identify the quantity to be maximized or minimized. So here, I draw the picture. So I have a box, and this box doesn't have a top because it says it's an open top. And what else we know is the length of the base is twice the width. So if I use a W to stand for the width, then the length L is equal to 2W, and the height I use H to identify. Okay, and now I want to determine which quantity I'm going to optimize, because the problem says to find the cheapest cost. So in this problem, the quantity we are going to maximize is the cost, of making this box. And here, since we're looking for the cheapest cost, so we are maximizing the cost. Okay, once we know this, now the next thing is to find the function, to find what is the cost function. So I use a C to stand for the cost. Okay. Now, next, I want to use the information I'm given in the problem to try to find the function of the cost. Because it says the material for the sides cost $5 per square meter, and the material for the base cost $10 per square meter. So this tells me the different part of this box, it costs differently. So if we if we cut the box, so there will be 5 parts. This is the base, and these are the 4 sides. Okay. So the base, the material, the price of the material for the base, it costs $10 per square meters. So right now, the area of the base is the length times the width, and because the length is 2W, so the area of the base is 2W squared. Therefore, the total cost for the base gonna be $10 multiplied by the total area of the base, which is 2W squared. Okay. So that's a 20W squared. Okay, let's Then let's take a look at the cost for the for each side. Okay, so the cost for these two sides for each side, the area is the width times the height, which is WH. So the total area of both sides is 2WH. And because the cost is $5 per square meters, so the total cost is $5 times 2WH. So it's 10WH. Okay, let me graph this. And we still have two sides, the front side and the back side. Okay, the area of each side is 2WH. So the total area is 4WH. And the cost for these two sides is also $5 per unit square. So the cost for the front and the back side of the box is 20WH. So since we can combine these two terms, so the cost is 20W squared plus 30WH. Okay, so I want to minimize this this cost. This means I want to find when W and H equals which number, the sum of this gonna be a minimal. Okay, let's go back to look at the strategy. In step 3, we wanna identify the constraint. This says there is a relationship between the variables in this quantity, and we want to find out that relationship. Why? Because using that relationship, we can reduce the number of variables in this expression. So let's go back to the problem to see what else we haven't used yet. So the first sentence says the volume of this box, because the storage container with an open top is to have a volume of 10 cubic meters. So this tells me the volume of this box is 10 cubic meters. So what is the formula of the volume of this box? The volume equals the area of the base and multiplied by the height. And since the length is 2 times of the width, so it's 2W squared times H. So the volume of this box is 2W squared times H. And because I know that this volume equals 10, so the equation 2W squared H equals 10 is the constraint in this problem. Okay, once we found this, then we use this constraint to reduce the quantity to one function having a single independent variable. Because from this equation, If we solve for h, then we can write h in terms of w. So now the cost we can write into 20w squared plus 30w times h, which is 5 over w squared. Therefore, the cost, we can express the cost as a function of w. In this function, we have only one variable, and that variable is w. Since we want to minimize the cost, so we're looking for the minimum value of this function. Okay, just like the previous example, before we start, let's think about what is the domain of the function. In other words, we need to think about how small w can be and how big w can be. Since the w is the width of the box, so it must be positive. And it can be as bigger as possible, because if the width is very big, so the box, we can think the box will be very like the height will be very thin, and also the length will be very short. So looks like when w is very big, so the box, we can think it looks like this. Okay, now next, with to find the minimum value, let's take the derivative first. So the derivative is 40w minus 150w squared. Next, to find the critical point, we let the derivative be 0, so we have 40w minus 150 over w squared equals 0. So we have 40w equals 150 over w squared. So if we multiply w squared on both sides, we're gonna have a 40w to the third equals 150. So w to the third is a 150 over 40, which is a 15 over 4. So w is cube root of 1, w equals cube root of 15 over 4. And the derivative does not exist. The derivative does not exist when w equals 0. However, since 0 is not on the domain of the function, so therefore this is not a critical point. So in this problem, we have only one critical point. That is a cube root of 15 over 4.